It's a pleasure to be here. I'm glad this foundation exists, and I've been invited to come and speak. How many mathematicians are in the audience? How many physicists are in the audience? How many bioscientists are in the audience? How many engineers are in the audience? Well, this talk's for you two. This is an engineer. Everyone else is dismissed, or you can go snack. This is an engineering talk. And what I mean by an engineering talk is that at least we believe, until we discover otherwise, that the physics that we're trying to take advantage of is understood. And that the experimentalists who are trying to implement the kinds of ideas that go under the general name of quantum computing are just trying to get working something which is understood quantum mechanics. Then there's another aspect which I'm not going to be talking about, which is, maybe even arguably more interesting than this, which is trying to understand the implications of quantum mechanics for information processing, and what does it mean to say that things are entangled or in a superposition, or kind of some of these words you hear associated with quantum mechanics for the world of processing information. But we experimentalists are several chapters back. Okay, we're trying to get things to work in the lab that are at the kinds of ones and twos of these objects, where there really aren't any open problems in physics. It's just excruciatingly difficult to build the machines themselves. So in that sense, it is an engineering talk. What's nice is that when you start doing this engineering and it doesn't work, often it turns out, as you'll see in this talk, that it fails to work for interesting reasons. It's not that it fails to work for kind of like the reason why the Chevy Volt battery gets too hot or something like that. Which, is an engineering problem and a profound one, but sometimes you discover things, let's say, that can be published in physical review letters that are the failure modes of these approaches. Okay? So the question of what we're trying to do is an old and interesting one, recognized really from the earliest days of quantum mechanics. And I think you can state it in the following way. Atoms and molecules give every indication of a physical theory that's well understood and that describes their behavior, in which the electrons that surround the nuclei of atoms and molecules behave like waves of probability, which, for those of you who don't think about quantum mechanics every day, I don't want to have this picture, for instance, just the simplest thing of a hydrogen atom with this cloud of an electron. That cloud is not a delocalized electron that's a fuzzy cotton ball of charge. Our interpretation of that cloud is that it is a probability wave. A probability wave that says, if I detect an electron, I get the whole electron right there with some probability. And instantaneously, the probability of it being anywhere else in the cotton ball goes to zero. Okay. So it's a kind of a funny business about this probability of detecting a particle at a certain place. If you put a whole bunch of atoms together, you get an entirely different theory of the world. Namely, the world of classical dynamics, mechanics, electricity and magnetism, Maxwell's equations, gravity, etc., in which things are sort of as they seem. I mean, you're really actually there. Yep, okay, I think. He's there, you heard it. The microphone captured the sound. There was no probability. The probability was, there was probability, it was unity, that I would find him there. Now, of course, he and the cat of Schrodinger's equation are made out of atoms. So what happened when you started putting 2 and then 20 and then 200 and then 2 million atoms together to the rules that govern how 1 or 2 of them behave? Okay. That's the subject of this interesting problem that surrounds my talk. So I'm going to just read it to you because it's nice. This is translated, of course, from German. But if you haven't heard the story, I don't know what rock you've been living under, but the story of Schrodinger's cat is something like this, and I'll just read you directly from the text. One can even set up quite ridiculous cases. A cat is penned in a steel chamber along with a Geiger counter and a tiny bit of radioactive substance. So there's the radioactive substance. There's the, well, we haven't gotten to that part yet. Perhaps one of the atoms decays, and if it happens, the counter tube discharges and through a relay releases a hammer which shatters a small flask of hydrocyanic acid. There's the acid in the bottle. And that would kill the cat if it decayed. The wave function of the entire system would be expressed by this, would express this by having it in the living and dead cat, pardon the expression, mixed in equal parts. So this is designed to illustrate this idea that we are living in an unfamiliar world, in the world of atoms, that is the world in which there could be a probability of something being in one state or another state at the same time, and that doesn't reflect our ignorance. It's not just that, you know, where are my keys? Well, they might be in my pocket or they might be at home. They are somewhere, I just don't know where they are. That's not what quantum mechanics is about. Quantum mechanics says that there is a probability that is finite, and if you find them on the counter, they could have been at home, but now they're suddenly not. Okay. It's a very funny theory. And we don't see cats doing this. We don't see cats suddenly appearing and disappearing, just like our audience members. But you know, this was a tricky setup. And it was a tricky setup because the conditions under which, physically, that cat might be made to be in multiple places at the same time, like no air, ultra low temperatures, etc., would surely kill the cat. So the cat couldn't live under the conditions in which such a superposition of states would be possible. But if we just change the problem a little bit to replacing the cat with a computer chip, we could certainly imagine a computer chip filled with billions of transistors, like everyone's got, you know, probably in their pocket or in their backpacks right now, all working, all connected to each other, all doing the kinds of things that the cells in a cat might do, except they're doing it using a different material, a man-made system that happens to work perfectly well at absolute zero. That is, you can make a transistor and it will turn on and off all the way down to zero temperature. And so the question becomes live again, or live and dead again, when we can start making billion transistor objects in which every state can be in a superposition of various states. So again, to now just go all the way down to the essence of the problem, to the 1-bit level inside of the computer, we think of a bit as being, you know, one of two possible states, which we can represent as a 0 or 1 in computer science notation, or we can represent as the state of a spin 1/2 object up or down. And quantum mechanics allows the state to be described by a superposition of the two possible states. And now we have this image of the inside of a computer being composed of, let's say, a bus of all the variables inside of the computer, the state of every transistor in the computer, superposed with every possible combination of all of those states, simultaneously coexisting, and until measured, all equally probable, let's say. And one more added twist, which I kind of already said when I gave the example about the keys, that your keys are at home or suddenly, because when you found your keys in quantum mechanics, not in the real life, in quantum mechanics, when you found them in your pocket, they had to suddenly vanish from home. And the question is, how long did it take the information to get from your pocket to home so that the keys could vanish? And how would Einstein feel about this from a relativity point of view of the information getting there? And the answer, as far as I understand, is that at least in the experiments that have been done, for instance, if you take the configuration of two states of a photon, or you can imagine it here with two states of an electron, spin in opposite orientation, like the ground state of the helium atom, and you separate them by a long way. If you measure this one, say, to be down, then this one suddenly becomes up. Now, what's very interesting about that little simple setup of the up and the down is I could have measured this one to be, say, east. I could have rotated my detector to be pointing in an easterly direction, which means that this one, once measured to be, say, east, instantaneously becomes west. So this object has to know what measurement was performed on this object. And you can imagine them being light years away from each other and suddenly getting information. How long does it take? Does it take the time that speed of light propagates? No. It's instantaneous. It's instantaneous transmission of something. I'm not going to say information, because you can't send a message this way. If you look at the outcomes that are measured over here, they'll look random. Only afterwards, when you put them back together, do you see that the random events on one side and the random events on the other side were 100% correlated. So you don't get to send a message faster than the speed of light. But you do.
Well, I'm not an expert in this, but
Yes.
I'm a little surprised at your assertion that it's that way. That's the way quantum mechanics describes it. But, for example, you couldn't do an experiment that would say it's like that and not traveling at the speed of light because it's really quantum field theory. Right? In quantum field theory, it wouldn't be instantaneous. Right? There's a causal relation between measurements, and I think you have to take that as...
No, I disagree. Yeah.
Well, we can discuss it.
So I would say that in quantum field theory, you would need to create for the case of passing information back and forth, there's a photon involved. Okay? There's no photon here.
No, but all I'm trying to say is that you're making statements about the theory that go beyond what the theory can predict. Unless you're going to tell us about an experiment that you can do that can tell us that it happens faster than the speed.
Yeah, there's a wealth of experiments. There's 200 experiments.
But not with the timing. Really? Okay, I'll listen with great interest.
No, unfortunately, I'm not going to be talking about those experiments. Those are because I'm going to be working on a microchip. But you know, the famous experiments of Alain Aspect and all these guys where they were creating entangled photon pairs and measuring one and seeing what the now you can say
this is called entanglement.
This is called entanglement.
But
Now
there's a point that it doesn't start in either place. It's not like, oh, you start here and you send a signal there, or vice versa. It is literally simultaneous. So there's nothing to travel because nothing's going anywhere.
Yeah, I only told the story in a sequential way.
Yeah.
In fact, it was only a correlation that existed.
Yeah.
No, I'm perfectly comfortable with the quantum mechanical description,
so
but
no
his
information is
statement...
being sent, and therefore...
Right, I agree,
contradiction.
but I'm also saying that his assertion that that's what happens, I think goes beyond what we can say.
Oh yeah. No, so your question really isn't not.
You
I don't
make
want.
a more detailed assertion than quantum mechanics.
Your
makes.
question is about experiment.
Yeah.
Your question is about what are the demonstrations that this is a statement true? Are there loopholes in those experiments?
Well,
No,
let's
wait.
discuss. I don't want to.
Yeah, okay, fine.
All right,
I'll
Charlie?
discuss
Yeah.
it afterwards.
Oh, sorry. Yeah.
Can you remind us or tell us what's the evidence for the existence of these things as probabilistic entities? In other words, everything you've described sounds like it could just be,
Wait.
we don't know the identity of these things. There's a pair. When you separate them, you open the door and look inside, you realize what the identity is, and of course that means the other one is the opposite because you knew they come in pairs. And
Yeah.
There's no mystery about propagation of information. So what's missing from that statement? What is it that establishes the probabilistic existence of these things in the first place?
Yeah. So there's a couple of. Let me back off of entanglement for a second. And I'm perfectly. This is great if this gets dragged off course. It means that the audience is at least awake, or at least a couple of people are awake. So let's consider this experiment for a second, which is not an experiment. This is a cartoon, but it's okay. There's plenty of experiments that are this one. They're small and complicated, but the experiment exists. Okay, and you let electrons pass through two slits at the same time and impinge upon a screen, and as time goes on, they arrive one at a time. Okay, now you could say, I just don't know which of the two slits it went through. That reflects my ignorance. And you would be uncomfortable for me to use this highfalutin language like it must have gone through both slits. Both slits simultaneously coexisted. You could just say, look, just because you don't know what slit they went through doesn't mean you can use fancy words like it went through both slits. And I would agree with you, except for the interesting thing that happens, which is when you let a lot of them go through, they make a pattern that looks for all the world to be a wave pattern that requires interference. And the fact that there's interference means that there's no story that you can tell in which you say there was like a spray paint can and some of the particles went through the left slit and some of the particles went through the right slit, and I don't know enough to figure out how the spray nozzle works to figure out which one. That story can't be true. It must be a story of every particle going through both slits. Okay. And what makes it maybe a little bit weirder, but it doesn't really change the essence of it, is if you're still not comfortable, let the electrons go once a day. Don't spray them out of the can. Let them go until they hit the screen. And then do the next one. And then do the next one. And you'll still get the same pattern. Okay, so that's, again, a beginning of the answer.
I thought relativity ruled out global clocks. If you can say something happens simultaneously everywhere, isn't that a global clock?
By simultaneously, I guess I would say, technically, I mean space-like separated. Meaning, it doesn't have to be simultaneous. It has to be on one of these, space-time diagrams of time and space. It has to be, and there's the speed of light, it has to be 2 points that are space-like separated so that no light could propagate between the two of them. So you have this whole zone to work in that you could say should give you a headache. Anything down here should give you a headache.
Why did you say that?
No one can see what I just wrote on the board. I'm sorry about that.
No, you could.
You can? Okay, fine.
In the cat, why did you say that for the Schrödinger cat example you needed zero temperature?
Because a little trouble spot in quantum mechanics, and I know I'm going to watch Pierre's face turn red while I start speaking.
If it hasn't turned red up to now,
Yeah, it ain't
not
gonna. Yeah, that's right. Then maybe you're dead already. Fine. That's my carte blanche. I can continue. There's a little asterisk in quantum mechanics about this wave business, which is the until you measure it point of view, which says that when you entangle your state with a large apparatus, then it becomes indistinguishable from that object being a classical system. Okay? Now, once it's classical, all of this stuff that I'm talking about, the interference effects, because there's a larger system that is still quantum mechanical, but I'm ignoring the larger system that it's gotten mixed up with and entangled with. When you're at finite temperature, that happens very quickly and readily. That is, phonons and all kinds of other disturbances mix with the system and become part of the system that you ignore. And the time that you've got to do the experiments becomes longer and longer as the temperature goes towards zero. How do you feel, Pierre?
no comment.
I want to just introduce a bit of notation that will come up. We generalized. I wanted to take those two states of up and down, or on and off, or 0 and 1, and I want to generalize them to say what quantum mechanics lets us do is create superpositions. And I want to invent a notation that lets me characterize the fact that I can write any kind of superposition as long as it's normalized with any complex number in the front, and that ends up being where you can point on the circle of a sphere. So these two can be complex value, but they have to be normalized properly. So any arrow on the surface of the sphere represents my switch. My on-off system now looks like an arrow on the surface of the sphere, and that's the superposition. And a nice result from computer science is that a kind of general purpose quantum computing machine, or a computing machine that takes advantage of the superposition states, or that allows the possibility of superposition states, can be made to be universal, that is, any function can be computed, with only two necessary ingredients. One, the ability, this is like a switch, a switch that you can flip a switch from on and off. So the analog of a switch in quantum mechanics is that you can change the direction that the arrow points. You can rotate the arrow to some other direction. The analog of a transistor, what's a transistor? A transistor is something where a voltage can control whether electricity flows. That's a voltage in a classical transistor. So this is the same kind of thing. This says that quantum mechanical state, whether it's up or down, determines whether that one flips or doesn't flip. That's sort of the quantum mechanical version of what a transistor does, but at the same time, that's the entangler. That's the one that says this state becomes entangled with that one because depending on let's say you don't know where it is on the surface of the sphere. If you measure this one to be up, that one will be up. If you measure this one to be down, that one will be down. So this is the entanglement engine, which is the quantum mechanical version of the transistor. And the rotator is the quantum mechanical version of the switch. And the nice statement is that that's all you need. That any kind of machine can be made out of just those ingredients, and you can make a universal machine out of it.
If you, it says if you put enough of them together and preserve quantum coherence.
Exactly. Yes, that's right.
Those are the ingredients, the only ingredients you need.
That's right.
You have to have enough of them
Those are
together.
sufficient, but they're not.
And they have to preserve the coherence.
Sorry, those are necessary, but they're not sufficient. They have to also be zero temperature or quantum fully coherent, and you don't need any third thing in the box.
What is fully coherent?
Say it again?
What does it mean to be fully coherent?
It means that the same statement that I made before, I'll do one more time, which is that the system has not mixed with any other outside agent to give the appearance that it is now classical. So let's say you built such a machine. Could you do anything with it? And the answer is that there are a handful, two in particular, plus their cousins, of algorithms that are known, and this is the most impressive of them. And what it says is that the particular problem of factoring the product of two prime numbers is one where there's an algorithm, and the algorithm reduces an exponential, a best known algorithm for a classical computer, which is an exponential function of the number of bits of the product of the two numbers, to an algebraic function. And so, using the fastest known algorithm, you can see that the problem when you get up near 1,000 bits becomes basically impossible to do, whereas with a quantum computer using this particular algorithm, it becomes easy. For any reasonable clock speed, it becomes easy. And this is where I have to say, I would say the great interest in this subject lies, but it's not my field. I mean, I wish it were, because I think it's a fantastically interesting problem, which is, like, what class of problems does that belong to? And what other problems are like that? And what other problems aren't like that? And I would like my bank account to be in an account in which the algorithm that's used to encode the information is provably secure from quantum speed up. But you can't even prove that. You can't even say that a certain algorithm is guaranteed to not be exponentially fast. So the whole question of what are the broad categories of problems and their relationship to known hard problems in computer science is an open topic and fantastically interesting, except for the little issue that it's now been 20 years and there has been very little progress in the field. Okay, so except for that little caveat, okay, maybe the mathematicians in the world consider progress on the 20-year scale would be sort of like a homework problem or something. But
it is not clear that it is possible that there is a fast classical algorithm.
Absolutely. I mean, it's not clear that any of the complete problems don't have a fast classical
I think
algorithm.
it's likely. I mean, it's not.
It's not.
It is likely.
It is. In my opinion,
Yes.
it's not. It's likely.
It's likely that there is a fast classical algorithm.
That means he wants to make a bet.
That's a methodology.
I have a feeling, you're a mathematician?
Yes.
I think, I have a feeling like in the mathematics circles, it's my opinion is a technical term. Is that true? I mean, that's sort of, there's like probably like reams of paper behind
There
what
are
you
no
just said.
results indicating that such an algorithm does not exist.
Correct. I think that as far as I know, there are no results indicating that a fast algorithm doesn't exist. Why? Because there's no algorithm, a fast classical algorithm that solves NP-complete problems doesn't exist.
The question
So-
is, how many euros would you be willing to bet?
Okay, let's press on because I'm a poor experimentalist who is over my head when it comes to these kinds of topics. This is an interesting question, though, which is of the same ilk that we've been discussing, which is, what kind of algorithms might exist, and it's another way of phrasing the question, which is, what is the source? What is the essential ingredient in this quantum mechanics problem that gave rise to the speed-ups in these algorithms? What could you take away from quantum mechanics? Imagine a universe that we don't live in, where you took away some element of quantum mechanics. Like, for instance, maybe you could have single particle interference, like the thing going through the slits and making interference, but you took away two particle entanglement. Then you'd have some world that we don't live in, but you could ask, would that world have Shor's algorithm for factoring, et cetera? And it's a nice answer that this paper gives. I'll just take it from the conclusion of the paper, which says, we're at the end, it's from the end of the paper. So it says, we're at the end of our search for the source of quantum effectiveness, and one conclusion can safely be drawn. There is at present no single reason behind the quantum speedup. Most likely the answer will intimately be connected with the exact nature of the problem, and as seen above, will vary from problem to problem. Though possibly intellectually displeasing, this answer is the only one, the only possible consistent one at present. So it's not really known. I guess that's a long way of saying we don't know. He doesn't know where the source of speed up comes from, or that it's different in each of these algorithms. So that there's no universal rule that says it. Sorry, no. Okay. But I want to just motivate this by saying that it would be, there are a lot of problems for which having faster computers would be extremely useful. I came across recently, now this is where the molecular biologists can help me, that there was a protein folding problem in which obviously the protein itself can figure out how to fold in a few nanoseconds less. And they had commandeered thousands of people's computers to run these algorithms on. So it was something like 10 million CPU hours, and they had found this very nice folding algorithm. And it really does make you say, well, and that of course is a quantum mechanics problem of how the thing will fold and find some minimum energy. And you think, that simple little molecule knows how to do it in a nanosecond. Why can't we figure that out? Why do we need 10 million CPU hours to figure it out? And I think that the answer is because it's a quantum mechanics problem. It's not a classical mechanics problem. And to solve quantum mechanics problems, you have to take a gigantic set of states into account, and it's too many for a classical computer to take into account. So if we could make a computer that had all of the same states available to it that the protein had that it was using, maybe we could solve those class of problems very quickly. So there are a lot of different experimental approaches to these problems, and I'm going to tell you about one. But I want to just mention that I'm one of 5 or 6 different kinds of approaches to taking a quantum mechanical system that you can get your hands on and control. Now, what I just said is the tricky part of this whole business. You have to get your hands on it and control, but of course you have to keep your hands off of it so that you don't measure it. But you have to be able to manipulate just the right amount to perform algorithms, but not so much that you measure the system. So this is the game that all the experimentalists are playing. How do you operate quantum mechanically with kid gloves that won't perform a measurement and decohere the system while still enabling you to carry out manipulations that you need to compute? So there are people who are doing it with atoms who are now miniaturizing their massive optics tables down onto chips so that they can scale. There are superconducting folks who make devices in which the direction the current flows through a superconductor, whether it flows in a clockwise or counterclockwise direction through these loops, represents the two-level system, which is the up or down arrow that can then be made into superpositions. And then there's the way that I do it, which is using spins that are inside of a box. So this is an important distinction. Before we represented the two-level system, which was a switch. A switch can be on or off, and we found that it looked like an arrow on the surface of a sphere because we could put in superposition states. And so it looked like a spinner of some kind. But I'm going to be actually using the spin of an electron as the two-level system, spin up or spin down. And so it didn't need to be, but that's a convenient one because it's not readily interacting with the outside world. When you take a piece of semiconductor material and you orient inside of it, even though it's disordered, you orient a spin inside of it, it can stay in that direction for a second or so before there's enough external perturbations coupled through spin orbit coupling or other kinds of effects that make the spin rotate, that the spin really does become untrammeled, by the crystal and by finite temperature, that you have a nearly untouched system. But there are knobs that you can use to control it, and that's what we're going to do. So now it's an engineering talk. Okay, so now we're going to figure out how to use the spins in order to control in a gentle way. So here's the engineering tool that we use. There's a fantastic strategy for making conductors that have almost no disorder. That is, the mean free path for an electron passing through this conductor can be much larger than the sizes of the devices that we're making, so for all intents and purposes, it's disorder-free on the scale that we're making. And the trick is to grow the material like rock candy, epitaxially, meaning one atomic layer at a time, and as you grow, everything falls into perfect crystal registry. Then change the crystal by changing the composition, adding, in this case, 30% aluminum to this gallium arsenide crystal, without losing the atomic registry. So it keeps growing where 30% of the gallium atoms become substituted with aluminum atoms. And the lattice spacing is such that it still keeps growing up without becoming disordered. Then you keep growing for a while. Then you put the dopants in, the dopants which will eventually provide the carriers. So in this case, they happen to be silicon dopants that live up here in this layer. But the gap, the difference between the valence band and the conduction band of the semiconductor is larger up here in the dark gray region than it is down here. So it really looks just like a ratchet. The dopants fall into this side. They fall into the smaller band gap material. When you pull an electron away from its dopant, there's an electric field that would like to spring back, because when you pull a negative charge and a positive charge away, they want to spring back toward each other. But if you pull it far enough away and then latch it like a ratchet on the other side of that smaller band gap, it can't get home again. It's stuck on the other side of the wall. So it leaves the ionized donors over here. The electrons are trapped on this side, up against the wall, and that wall is perfectly atomically flat. So it makes this very lovely two-dimensional, so-called two-dimensional gas of electrons that is disorder-free. The dopants are even remote, and so the Coulomb tails of the dopant sites themselves don't even disrupt. Now you do one other bit of engineering, which is you buy a tool that lets you write with an electron beam. This is a beam that comes just like an electron microscope, except you disable the rastering of the electron microscope and you turn on something that writes. You put plastic on the surface of the semiconductor, you blast it with the electron beam, it becomes soluble in some solvent only where you've written on it. That comes off in the solvent. You then put metal over the whole surface. It only goes where you've written. And when you take off all the rest of the solvent with acetone, you drop it in acetone, fingernail polish remover, and the whole thing comes off. And what's left behind is where you put the metal down on the surface where you wrote with the electron beam. And that is a technology that lets you make structures on a deep submicron scale. So this picture is about 1 micron from side to side. Remember that a human hair is about 60 microns in diameter. So you have very fine control over the writing, and you can make a little box that you can put electrons in. And it works like a charm. I mean, I'd like to say that this is, really, you should be very impressed, but you just throw money at it at this point. And the machine comes and you design it on a CAD system and you barely even know that there's an electron beam involved in the whole thing, but then, after you put the thing in the fingernail polish remover and it comes off, and you look under a really good microscope, you see, lo and behold, you've made this fantastic pattern that sits down at the bottom of the machine. So with this kind of a box shaped in this way, I can put negative voltages just connected upstairs at room temperature to batteries. And if I put a negative voltage on those metal gates that sit on the surface, electrons will not like to go underneath the negative voltage. They're repelled from the metal because it's got a negative voltage on it. So I can take my two-dimensional conducting layer and I can trap, in this case, for instance, 2 electrons. Now, how do I know that it's 2? I'll tell you in a minute. But let's say I trap 2 electrons in. And now I've made a little 2-electron box. The ground state of 2 electrons as I approach the 0 temperature is a singlet configuration of the 2 electrons. They are in a configuration of opposite spin. In fact, they're an overall anti-symmetric wave function, so they're up, down, minus, down, up. They have to have that minus sign in there so that the symmetry of the 2 electrons is preserved. It's just like the ground state of a helium atom, but now it's in a box that I've made. Now I have voltage control, so I can turn the voltages and I can separate the 2 electrons. I can make the ground state configuration instead prefer to be in the 1-1 configuration in 2 separate boxes. And I've made a little machine which took my 2 singlet-oriented electrons and separated them into 2 different boxes.
Without measuring them.
Without measuring them. Now, how do I know that I didn't measure them? That's what I'm going to spend 10 minutes telling you. The whole business of, did I just separate them and now their spin orientations are totally random, or what? And that was a hard experiment to figure out. What are they doing? And I'll spend some time telling you about it.
So what is quantum dot? This was quantum dot? Did you just describe this?
Yeah, in fact, I would call that a double quantum dot because it was 2 guys next to each other that you could separate like that. So this is what the chip looks like. This is just a photograph with a camera, with literally like a pocket Instamatic that you just get close to and just take a picture. No microscope involved in this one. So you can see that the chip is, kind of a 0.5 centimeter size thing, and there's no way you can see what's going on, but it's nice to see that the wires that are eventually connected to the ends of that piece of metal that come down to this micron scale literally just go through these wires to those bonds, which eventually connect to this kind of a commercial chip carrier that's at the bottom of a refrigerator that goes up to room temperature. And so you see the other end that you don't normally see, which is from these micron things, it just goes out to wires. And the wires go up through these, these connectors there. You can see the wires on their way up right there. And they go right up to room temperature where you can connect them to voltages. And if you want to make the thing go from 2 in one box to 1 in the other, you just change the voltages. So it's like a little atom that you can make, but where you make the potential yourself. Okay. So now how to measure and put these electrons in the box. Before we find out whether they stayed as a singlet, let's at least figure out how do we get 2 in the box in the first place. So what to measure? In this diagram, we have the double quantum dot right here, where this voltage in the middle controls the splitting between the 2 boxes on the side, so it looks like a double well potential. But along the sides, there are other narrow constrictions. Again, that's a 0.5 micron, so this thing is about 100 nanometers wide constriction. And that's sufficiently narrow that when I measure the conductance of electricity through that little 100 nanometer channel, when I put 1 or more electrons in that box, it capacitively couples to the width of that channel because it's a semiconductor and changes the conductance by a few percent. So if I look at the conductance as a function of the gate voltage on voltage number 2 on this guy on the side, I see first of all that the voltage changes the conductance. Here's the conductance of this side, which is the right sensor, so the sensor on the right. And I see that as I change that voltage number 2, it starts to pinch off. But every once in a while, there's a little tick, 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 tick in the data. And that tick, tick, tick in the data is when an electron inside the box has been forced to exit. Because the box itself is getting to be a smaller and smaller potential, a less and less friendly place for the electrons to reside, and they're kicked out one at a time. I have the other side as well, the left side and the right side. I'll call these left and right now instead of 2 and 6. And I see that where those tick, tick, ticks are form a lovely checkerboard pattern of where electrons will enter the box. But what's interesting is that at some point, the pattern just ends. I keep going negative, negative, negative. I see the tick, 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 tick. And then no more ticks. And then I know the box is empty. So now I can unambiguously label that box as 0, 0. The left side is empty and the right side is empty. Now, if I turn up the voltage more positive, making the potential deeper on the right side, I get a tick. Now I can unambiguously label that 0 on the left and 1 on the right, or 1 on the left, 1 on the right, etc. And I can just count how many ticks have I gone over. So this intersection is where I want to pay attention now. This is the intersection between none on the left and 2 on the right, and 1 on the left and 1 on the right. That was the little entanglement picture that I showed before. 2 on the right goes to 1 and 1. Now it tells me where to tune my voltages so that I can just move between those two worlds. Let me not take a derivative which emphasizes the transitions, but let me just show you the actual raw data itself, which is the measurement of the conductance through that sensor channel, and I'm color-coded it so you can see that the conductance changes, and now I can just read off from that sensor what are the states. So here's the voltage range for that configuration and the voltage range for that configuration. And now we can start doing our entanglement experiment. So let's do the following. Let's start over here somewhere with 2 electrons on the right and none on the left. And I'll draw it in this kind of schematic way, like electrons with blue balls. I'll put 2 on the right and none on the left. And I also want to introduce a diagram, which I introduce a variable called epsilon, but epsilon is just the tilt. You know, if it's 2 on the right, then epsilon is positive. And when I go to epsilon is negative, it goes up to this end here, so epsilon is just a variable that goes along that diagonal line. So now the O2 configuration is the lowest energy state, and the 1,1 configuration is higher in energy. When I move to negative epsilon, by moving to that voltage range, the 2 electrons separate. And I can go back. Now, I had said that the ground state configuration was this particular singlet state. And I'm going to draw the diagram in a slightly more complicated way, indicating now singlets and triplets. The singlet state will have an anti-crossing because there's a singlet over here and a singlet over here. And right in the middle, I shouldn't describe it as an O2 state or a 1,1 state, but I should in quantum mechanics say that it's a superposition of O2 plus 1,1 and O2 minus 1,1. And that transition produces this anti-crossing, and it's anti-crossed by the rate of tunneling. If there was no tunneling between the two sides, then I would say it's either on the left or on the right. It would go flop or flip on the two sides. But if there's a finite rate of transition between the two, then I anti-cross those two. Notice there's no triplet anti-crossing, and that's because the triplet of O2 is out of the picture. It's very high in energy, just like the triplet state of helium is very high in energy. On the scales of these problems, the triplet state is out. So there is no triplet of O2. If I try to put 2 electrons in this box, they must be in a singlet state. The triplet state is much too high in energy to ever be accessed.
So if this is necessary if you want to do quantum computing and you want to put in an entangled initialization state.
Well, I wouldn't say it's necessary. I say we got lucky. We got lucky because nature chose to have the ground state of a system being an entangled state.
Right,
Had I, for instance, used a single electron, then the ground state just would have been, say, aligned with the magnetic field, whereas the excited state would have been anti-aligned, and I wouldn't. So by using 2 electrons and by taking advantage of the fact that in low magnetic field the ground state is a singlet, I get my entanglement for free.
Right, but if I generalize it to
Yes.
real quantum computing
Yes.
or n bits, then
Doesn't get
this
any
doesn't
realer
work.
than this.
Right.
I'm not going to say this is real, but this is as real as it gets.
No, but how do you do initialization in that case?
Oh, you mean like to a whole register?
Right.
two at a time.
Okay.
Yeah, you have to construct such a system in which you either start at the ground state, whatever that may be, and manipulate from there, or
You need to make sure that the transitions are always in the right way.
yeah, that you have to just set it up. So our initialization problem is easy.
Right.
Otherwise, you have to manipulate in order to initialize. Okay. Now, this was the experiment that I described before. You separate the two, but now they're a singlet that I've separated. And now the key question that you asked was, are they still a singlet once I've separated them and they're no longer energetically constrained to be a singlet anymore? Now they're just two free isolated spins that could be anything that they wanted to be. And so I'll represent that question in the following way. After some time, these systems can mix. They might not be a singlet anymore. But now I have a clever way of finding out whether they are still a singlet. And that is to try to put them back in the box where they came from. If they go back in the box, they must be a singlet. That's the only one who fits in the box. If they don't go back in the box, they've rotated themselves out of the singlet state, and they're not a singlet anymore. They're stuck in 1-1, one of the triplet states, and they can't find their way back into the box. And that measurement will tell us what has gone on. So this is a busy slide, and I'll do the easy part first, which is the engineering side. It's a little more complicated than I said with just the wires going up. There's a lot of microwave equipment that's necessary, and for those of you who like this kind of stuff, we can talk about it afterwards, but we build, instead of just measuring the conductance, the best way to do it quickly is to actually build a resonance circuit down here, and to see when the resistance changes a small amount, it shifts the Q of the resonance circuit a little bit, so you can do it fast as hell. Instead of having to measure with DC what the resistance is with an ohm meter, you can do it with a resonance circuit. And all of that is supposed to make that work. But when we can measure fast, then we see an interesting thing that happens. This scale, the horizontal scale on the top axis, is how long I keep them separated before I try to put them back in the box where they came from. So if I keep them separated, as quickly as I can take them apart and put them back together again, so I make the singlet, I separate them, and I quickly put them back together again. It's like the rule where if you drop the candy on the floor, you've got 3 seconds to pick it up. This is like the 3-second rule. So if you quickly put it back in the box again, it all goes back in with a certain voltage that I can associate with the singlet state. That is, it's the state associated with 2 electrons in the box, and I get a singlet. If I wait 50 nanoseconds, almost nothing comes back as a singlet. But interestingly, if I wait about 100 nanoseconds, it all comes back again. And then 50 not. These are the results of single shot measurements where I create, separate, wait, recombine, detect, throw out, reinitialize, separate, wait, recombine again. Each spot is 100 measurements. And then averaged, all of them, and then there's the result of all of those groups of 100 measurements. And it's very interesting to see what's happening, which is, first of all, obviously, there's some oscillation going on. Second of all, you may notice, if you have a keen eye, that the period is not constant. It's getting a little shorter over here after, this is real-time measurement in the experiment, including measurement time. This was just how long they were separated. But after 50 milliseconds or so, it ain't the same precession rate as it was before. So what's causing the precession? Who's messing with our singlet? And the answer is an interesting one, and it has taken us several years to map this all out. And this is where I said, sometimes the bug in your engineering problem turns out to be a very interesting physics problem. The nuclei of the gallium and the arsenic atoms are coupled to the electron spin. There's a spin-spin interaction between the nuclear spin and the electron spin. And so when I separate the 2 electrons, the cloud of 1 million or so nuclei that one electron sits over is different than the cloud of the 1 million nuclei that the other one sits over. that collective so-called hyperfine coupling between those million nuclei in this stack and the million nuclei in that stack look to the electron like a local magnetic field. But because the nuclei are at high temperature, that field is a random object that points in some funny direction. And it precesses around the local magnetic field. So however strong the local magnetic field is, there are these two precessions going on. You started off with a perfect singlet, but after some period of time, they have precessed themselves right out of the singlet configuration. But the interesting thing about precession is just wait, it'll come back around. But now what's interesting is that after some 50 or so milliseconds, the rate at which it's precessing changes. And that's because the nuclei themselves have rearranged themselves. Why have the nuclei rearranged themselves? Because they themselves have nuclear-nuclear dipole interactions between the nuclei. And they are coupled via virtual excitations of the electron spin. So there's this interesting physics problem, which is a million spin a half, or in this case spin 3/2 objects, it's just as interesting with spin 1/2, each coupled via one spin to each other, virtual excitations of that one spin. They don't even need to have direct dipole-dipole interactions. In fact, this virtual interaction through the electron spin dominates the rate. So this poor electron is sitting there trying to be by itself. It's processing around this nuclear problem, but meanwhile it's being used as a medium through which the nuclei can interact and themselves evolve. But you see they're doing so slowly. They're evolving on an entirely different time scale than the precession. The precession rate is at tens of nanoseconds rate, but on the millisecond rate, the nuclei are evolving. So this is a really interesting physics problem now. Let me cast our new problem into the form of this so-called block sphere, or this two-level system. I have two states, and I initialize into one of them the singlet configuration, up, down, minus, down, up. Now what I would like to do is let it precess into the other state that's available, which is, I'm going to separate the other two triplets away with a magnetic field. Let's get rid of those guys. There's only one other triplet state. And how I'm going to represent that precession is in the following way. The two different magnetic fields on the two sides cause a precession between the singlet and the triplet. But notice that the energy difference between the singlet and triplet is what we would call the overlap of the wave function between the two. That's the thing which is very big in the O2 configuration and which goes to 0 in the 1-1 configuration. That's another field on this problem. So it's like I have a spin-a-half system. The spin-a-half system is actually made out of two spins. It's the singlet and triplet configuration of the two spins. And there are two orthogonal fields on that system. One which points in the z direction, which is the exchange interaction, something I control electrically. And the other one which points in the x direction, which I don't have control over. Nuclei are causing that field. And the reason I get this very orderly precession is because I'm moving this way around the x-axis. When I turn on exchange, I go this way around the z-axis. That's the exchange field. So now I've reduced this whole problem of nuclei and exchange and singlets and triplets onto this sphere. But now I can really go to town. For instance, watch the following process, which you see it's a little bit complicated. But from my point of view, these are just voltages. You just program the computer to put out the various voltages. But let's follow the picture on this diagram, which I think you're now an expert at looking at. The vertical axis is epsilon. That was our tilt. When epsilon is positive, we go to O2. That's how we initialize. So we start off initializing into the state of the singlet. So far, so good. I separate the two quickly. I'm still in the singlet state. I let the system wait. What happens? Over an ensemble of nuclei, I begin to precess around the x-axis of the problem. Those are the nuclear fields that are causing the precession. And I start to precess like in this direction. The ensemble spreads out over some cone because sometimes nuclear fields are bigger than others. But right in the middle, I turn on a field in the z direction for exactly how long it takes for that whole plane to precess by pi. And it flips around by pi. Now, all the ones that were in the front of the race are in the back of the race. And the ones that were in the back of the race are in the front of the race. And they continue to precess to the extent that these are the same nuclear fields, and everybody reassembles back up at the North Pole again. Just like if you tell runners on a racetrack to stop, turn around, and run the other direction, the fast ones were in the front, now they're in the back, and they all end up crossing the finish line at the same time, assuming they run the same race. So as long as these two situations have the same nuclear fields, you've now taken the nuclei out of the problem. The principal source of decoherence of the electrons once separated has now been removed using a technique well known in NMR called spin echo. And they're out of the problem. Now what's interesting is if you're tempted to do spin echo, which I'll call this a pi pulse right in the middle, why not generalize it to what's in the NMR field called the Carcell-Echo sequence of adding pi pulses every period. So now this is my pi pulse. I would prepare, separate, put on the exchange field for exactly pi, and then measure at respectively P, S, E, and M positions. I can put in all kinds of pi pulses. If I'm worried that the nuclear field here and nuclear field here may not be the same, just make the interval shorter. And now this is remarkable. The coherence time, or the probability of coming back as a singlet, now, even though in 10 or 20 nanoseconds I precessed out of the original state, now I see 3 to 4 orders of magnitude, meaning it's precessed 1,000 times around the racetrack. I flip them, and they exactly unwind and come back to where they were. And I'm now up at 60 microseconds for the characteristic time. So by taking old-fashioned techniques like Carcell echoes and bringing them into this modern world, I can do the same thing that they did with NMR, which is I can remove inhomogeneous broadening, and I can start to measure the real decoherence rates associated with these nuclei. Let's do the next hardest thing. Thinking like Moore's law, right? Well, if it's Moore's law and it's really exponential, I should go from 2 to 4 to 8 to 16. Well, I'm sorry. This is going to be linear Moore's law, where we're going to go from 2 to 3, and then we're going to go home and rest. Okay, but we can at least make a box now where we can put 3 electrons, 1, 2, 3, and the diagram of where these transitions are gets correspondingly more complicated. But after a while, you can start to identify, using these proximal sensors, exactly where electrons are in each of these boxes. So here's 2 on the left, and none in the middle, 1 on the right, etc. Here's 1, 1, 1. That's what 1, 1, 1 would look like. Now, why would I want to do this? Well, let's of course.
But if you do so it goes exponentially, so it's still zero, because you have now to identify 8 states.
That's right. Well, that's right. It could be that the next one is, like square root of 6 or whatever. Yeah, right. Okay. So, you know what? I have a feeling like this is going to be slower than the development of the classical computer. I'm not sure why. Maybe that's where the exponential speed up catches you, which is that they're exponentially harder to make these systems. That may be how the whole thing ends up playing out. Let's do a first interesting experiment where instead of using nuclear fields to rotate the spin, I'm going to use another spin to rotate the spin. Let's do the following. This should look exactly like what you've seen before. Here is 2, 0, 1, which means I've got 2 electrons in a box, then a nothing in the middle, then 1 electron over the side. This guy's just sitting here by himself. He's going to be used in a second. But you know what's going to happen. These 2 are going to make a singlet, and then I can separate them. But then I'm going to do something very daring, which is I'm going to go, not just to separate them, but I'm going to go all the way over and kiss this guy. And then I'm going to run back home again. So it's going to look like this. I separate near 102 until these 2 wave functions overlap. And then I run back home, and I see, can I go back in the box? Did coming over here and touching that spin make another kind of rotation? And the answer is yes. So just, I mean, it's raw data. This is now we're like modern. This is unpublished stuff that we're still in the process of taking, so it looks a little bit raw because, in fact, it is raw data. But here's, as a function of how far I went over toward that other spin, the probability, this is 1 minus the probability coming back. This is the probability of getting stuck in the other one. And I'm just reading out the voltage on that proximal sensor. And now this is very interesting because what it says is that at first I don't get stuck. I always come back. That's the short time candy rule. Okay. Then I get stuck when I've gone over and the interaction with the other spin has made a pi phase shift, and then I get stuck all the time. And then not stuck, and stuck, and not stuck, etc. And by going farther and farther, I can go out to something like 132 pi's of going around before I come back. The separation time was 2 nanoseconds. So I want this to put in your mind the scale of operation, which is I can in 2 nanoseconds create a multi-pulse, but I've got on the scale of 40 or 60 microseconds, okay, that's 4 orders of magnitude longer, 4 orders of magnitude and a factor of 2 longer, between how quickly I can manipulate and how long my coherence time is. Now, there's all kinds of interesting things in these data. Why there's a little pinch point here? The reason that there's a pinch point there is because this is the place in the middle of that diagram where the exchange is changing rapidly. I think I put this picture in. I'm going to skip over this a little bit. But the exchange is changing very rapidly, so that as I move faster, you see the period is very quick. If I go just a tiny voltage more, I go another 2 pi. But that's also the place where I'm most sensitive to the outside world. So decoherence is the size of the envelope, and it's proportional to the frequency with which I advance. So there's all kinds of interesting things which I didn't have time to get to. I want to end with another approach. This is an even more engineering approach. You see, because as a physicist, even though I set out to do an engineering problem, I got kind of fascinated with this nuclear physics problem and thought that it was kind of cool. And the real engineer would say, don't get distracted by physics problems. You got a nuclear problem, get rid of it. There's plenty of materials to choose from in which there's no nuclear spin at all, like carbon, or one favorite is how about silicon. 90-something%, 96%, 95.4% of silicon is 0 nuclear spin. So the other half of my research group is trying to get out of the materials that have nuclear spin and using all kinds of other interesting things to do. And I'm going to mention just one, and then I'm going to end my talk. The one I'm going to mention is a carbon nanotube. And a carbon nanotube is particularly interesting, first of all, because it's made out of carbon. I'm probably the only person who is selling carbon nanotubes, not for tennis rackets or for modern electronics or for bioassays, but because it's made out of a material that has 0 nuclear spin. But that's why I like carbon. You can do the same thing that you did before, which is you can make all kinds of gates across the nanotube. In fact, the nanotube is only a few nanometers in diameter. You can't even see it in the picture on a 1 micron scale, but it's there because it conducts electricity. And by putting voltages here, you can confine it. We can use the other end of the nanotube as the sensor, because we can make a transistor out of this thing and connect it via this orange piece to the other end. And then we do the same thing that we did before. We start measuring on the sensor as a function of the left and the right gates. And all of a sudden we get to the place where the pattern stops. And we've got an empty segment of electron-free nanotube that we can then make a quantum dot out of. And we can continue to do these kinds of stuff. Now, for the mathematicians, I wanted to mention an interesting problem which is related to these carbon nanotubes. Now, it's not really a math problem yet, but I'll just explain it in an interesting, or what I think is an interesting way, mathematically. When I apply a magnetic field, which I was using before to split these levels off, The nanotube cares whether the magnetic field is down the axis of the nanotube or whether it's perpendicular to the nanotube. In fact, if I look at how the levels split and separate, in a perpendicular, or in a parallel magnetic field down the axis, they split very rapidly. And when it's perpendicular, they barely split at all. Now that's interesting in the context of a bent nanotube. Let's imagine that I take a nanotube which is bent in an arc, and I put an electron here. Now as I move the electron around using gates, the static magnetic field has different projections onto perpendicular and parallel. And so the splitting will change as a function of position. Aha! I've coupled position and spin. So all I have to do is move the electron, and it thinks it's in a different magnetic field. Remember before we were using magnetic field gradients to do the control of the spin? Now I've made an effective magnetic field gradient which I can control with a voltage. So everything before where I had to have the nuclei doing work for me, now I just have position. Again, gate voltage controllable. What's nice about this is in a straight segment of the nanotube, there's no effect at all. You move along a straight segment, magnetic field is constant. You get to a curved segment, and the magnetic field turns, the space turns into effective magnetic field. You can even, on the curved parts, couple two different spins. Because if this capacitive coupling pushes an electron to some other location, it will raise or lower its energy depending on whether it's spin up or spin down. It will have no effect on the straight segments. So by using carbon, first motivated by the nuclear spin problem, I see that I get an extra new variable in my problem, which is the curvature. And curvature can now be used to intentionally couple instead of unintentionally coupling to magnetic fields. I'm back to being able to use voltages, and once I can use voltages, it's all able to be done experimentally. There's a whole other story about silicon and doing these kinds of things, which I'm going to skip, and I'm going to now just stop at the end of the talk and say, let's review this long, shaggy cat story that started with the problem of a many electron or a many particle or a many quantum dot or a many transistor system behaving like a quantum mechanical object, and us bringing it down to the level of just creating our first entangled pair and measuring how long we've got, and discovering that nuclei, the substrate of the experiment, was playing an important role. And we could see the oscillations and understand how the nuclei were participating. And finally, I didn't have a chance to talk about silicon germanium, but there was also this migration into other materials that helped us to avoid one interesting problem, but in a way discover other interesting engineering aspects that surely will have interesting physics as we start moving objects around in curved space in these systems. So that's the end of my engineering story. Thank you for your attention.
Okay, so questions, Carmen?
Yes, Charlie, you showed us some decoherence times. How do those observed decoherence times compare to what you need for error correction?
Okay, so there are these very simple criteria that say there's something called an error threshold. And the error threshold is expressed in this dimensionless quantity of how long the coherence time is divided by how quickly you can do operations. So something like the number of operations you can do. And when that number gets to be of order 10 to the 4, it has been shown that you can correct errors by scaling the system to larger size. That is, you can introduce ancillary quantum bits that will measure and correct on the fly. If the error is too large, then introducing ancilla only make matters worse. So there's a threshold for scalability of the systems that have this kind of magic dimensionless number, which is of order 10 to the 4, and which depends on implementation. And some people argue maybe it's 10 to the 3, maybe it's 10 to the 4. We're pretty far away from needing to know that, and so it's going to be algorithm dependent, but I think that a good rule of thumb is you get happy when that number's on the order of 10 to the 4.
Right, but where are you now? I guess is the question.
We're now at 10 to the 4 because we had this, let's say on the order of magnitude, 100 microsecond characteristic time after we echoed compared to a nanosecond characteristic, a few nanosecond characteristic gate time. So if that was 20 microseconds instead of 100, so 20 microseconds divided by 2 nanoseconds is the 10 to the 4 that we were looking for.
That's great.
Yes, there was a question over there. Yeah.
Yeah. No, you. Yeah.
So I want to ask you if you believe that the quantum computer will be built at some point. Because I assume you believe it, but let me ask you, how long will it take?
You know, there's a company called D-Wave.
Yes,
So I could, if I said I believe in D-Wave.
You believe it even?
No. I said, I was careful what I said. I said if I believe in D-Wave, I would say there's already a quantum computer. Okay, now, the trick with D-Wave is, this is a quantum computer. You know, try to build this without quantum mechanics. This is a quantum table. Okay, there is no such thing as classical physics. Everything is quantum mechanical. So you mean a specific thing.
Superposition.
You mean a system which takes advantage of superposition to calculate, and, if I can put words in your mouth, stop me if I put the wrong words in, and can do a calculation that you can't do classically.
Faster, no?
Faster. I think it's more than 10 years.
That's all. Well, maybe that you can figure out. Just give it up.
All right.
I just gave a recent talk in which I said that, and people said, no, you're wrong. It's going to be done in 2. And I don't believe it. I think it's going to be done in more than 10 years.
Yeah.
Because there's a lot of engineering problems here. Just engineering problems. Engineering challenges, cool physics problems. But before that machine can do things faster than we can do classically, it's at least 10 years.
But less than 20?
I'm not answering that question. I don't know. I don't know. I don't know. I don't know.
Okay, so let's.
The answer is a superposition of 10 and 20.
Yeah, I don't know the answer to that question. I don't know the answer to that question.
So follow up on your decoherence ratio of 10 to the 4th. It reminds me of dynamic RAM. And there's a trick in conventional circuits where you double the number of transistors and suddenly you have static RAM. Do you have a trick you can do there?
Well, you know, one of the great intellectual breakthroughs in this field, which coincidentally is also attributable to Peter Shor, was the idea that you can do error correction without measurement. So there is I mean, you normally think, you know, error correction means you measure, see what it is, but then you say, oh, that's bad. I just killed the cat. Okay. So what Peter Shor showed was that there are very clever ways. I mean, you know, maybe the 2 key results of the field are attributable both to Peter Shor, both of these guys. But probably the more important one is the fact that you can do error correction without measurement. So I think that the analog is extremely close because it really does follow, you know, what do you do in error correction? The simplest way to do error correction is you double you introduce redundancy, and then you do parity checks and things like that. So this is almost the same thing. You take a bit, and you can't clone it, but you can make a kind of a copy of it in a certain way, and then you can then later do basically like quantum mechanical parity checks. I mean, in a way, my singlet measurement was like a parity check. Were they like this or were they like that? Okay, so by doing those kinds of measurements without actually projecting out onto one of the 2 basis states, you could do error correction. So I think the analogy is very close, but it's all attributable to this. I mean, I think that's really what got people excited, was because, you know, if these all had to be right out of the box, it would never work. It would never work. Then I would not answer 10 years. But if you could possibly take advantage of the mass production of semiconductor technology that says, you know, nobody's afraid of putting 1 billion things on a chip, even 1 billion pretty complicated things. That's not the hard part anymore. We've already passed that technologically. 1 billion, no problem. Okay. So if simply scaling to larger numbers of elements is all we need to do in order to beat decoherence, that's great. That would be a total victory. That's why people were excited about quantum error correction, because it says scale up the system, basically do parity checks on your data set, and you'll we correct errors, that's something that chip builders know how to do.
All right, so David?
Quite a few years ago, everybody was excited that a quantum computer could actually factor 15.
Yeah.
But somehow we've never heard of it factoring 21. Why haven't people sort of gone on to other benchmarks?
Well, I actually think that reflects a kind of a maturity in the field, not a stasis. I think that the maturity is that people kind of collectively realized that was a parlor trick, and although that was a fantastic first to show that you could encode numbers in quantum states, that's really what was going on. I mean, it wasn't about factoring; it was about encoding the numbers 3 and 5 and doing things like, even multiplication would have been impressive. It was putting a number into a spin and doing a manipulation with it. That was the cool thing, okay? And I think that what happened, okay, the reason why I say that it was sort of an act of kind of collective maturity was what has happened to that line is people said, well, that's fine. But that technology, which was a so-called NMR quantum computing, that's where that work was done by Ike Chuang and Lieven van der Sijpen and the guys who did this factoring of 15. Itself doesn't scale, and people stopped working on it, and funding dried up, and it became passé to do NMR quantum computing. And the reason why was because even though it had a head start, people could look ahead and say, ultimately, that one is not one where you can do this thing where you can make 1 billion guys, okay? And so they said, because maybe we'll be able to factor some next cool number, okay, but eventually it's going to dry up. And people stopped working on it. And they started working on things which were much more primitive. I mean, I can't factor 15, okay? But if we get this working, it has the possibility of being able to take advantage of this mass production and to scale.
Okay, so maybe with that, we want to thank Charles again for a great talk.